So sit back and enjoy. You're on mute. This HSW AIA accredited portion of our presentation, moisture management and residential facade design.
Without further ado, I'm going to introduce Lucas.
Thank you, Michelle. Bringing up my presentation now, and okay. Hopefully that all looks right and is in presentation mode. And if so, I will.
Doing good.
Great. Then I'll go ahead and kick it off. Welcome, everyone. Thanks for joining us today for this presentation. It is about moisture management and residential facade design. The presentation is credited by the AIA for Health, Safety, and Welfare credits, and is also copywritten by CertainTeed. I know that a copy of the presentation will be made available to those who would like one. And if there are any materials that are mentioned during the course of this presentation that you would also like to get your hands on, please let us know, because I will be dropping some references to some research material that's been found around the world with regards to this topic. And, you know, frankly, that's what we do, or that's what I do, is I scour the world looking for information about these strange things, because it's really hard to find in one place. And we, you know, at Saint-Gobain, we don't do research necessarily on these kinds of topics. We're a materials manufacturer. We're specializing in decarbonizing materials and doing all these kinds of things there. And we fund research around the world in all different kinds of organizations on these topics and let the experts chase this information for us so that we can turn around and help apply it or share it with you so that you can apply it and ideally create more sustainable, more durable buildings that help us all succeed. And, you know, in our existence of making buildings, moisture has clearly been the root cause of the majority of our issues when it comes to premature service life or building service. And so it's always a good time to stop and remind ourselves about water and all these cool things about water and how it affects our buildings, and go back and refresh ourselves on some basic concepts that tend to get lost in the noise of all the challenges which are put before us. The challenges of building design with regards to, you know, from aesthetic to energy performance to now sustainability performance to, you know, ultimately durability. Moisture is in the heart of all of these things, and so we should talk about it. So we're going to review some of the basic functions of the envelope. That'll go quickly. We're going to review some basic stuff about heat, air, and moisture as well. We cannot get into this conversation about how things get wet and how they dry unless we talk about heat, air, and moisture. It's kind of like the three favorite things of any building scientist to start getting carried on about, but we're going to do it again because to solve our problems, we have to first refresh ourselves about why they're happening. We are going to talk a little bit about some moisture storage properties of materials. And this is really, really important point of it, because buildings are going to get wet. The goal is to help them dry and dry at a rate which keeps them at a moisture level which is safe and that they can perform at. And then we'll look at different kinds of claddings and see if we can take this knowledge that we've accumulated to this point and apply them to different kinds of cladding assemblies and ways to improve them, or seeing things that we can tweak about them, or seeing things that we don't like necessarily about them with regards to this idea of draining and drying. So jumping right ahead, functions of the building envelope. I think you guys know this, right? It's structural. In most cases, the envelope is structural in residential construction. It is intended to protect us and be the envelope between the interior and the exterior, creating that interior environment in which people can thrive. If energy was free, that would be really easy, right? Back when energy was cheap, we didn't have nearly as many problems. We also had like 3 or 4 layers to our walls. And now that energy is expensive, we've got like 6, 7, 8 layers to our walls. And we find ourselves in a durability pickle. And so we're going to talk about how to get that durability back in, because that is one of the goals. It's a function of our envelope. Also, now the pressure is on us to be efficient and be sustainable. We can do all of this at once. It is possible. All the tools and the information are before us, but you know what ironically it takes is going back and remembering the lessons of our forefathers and our fathers, our grandfathers, the giants on whose shoulders we stand with regards to building buildings. They did things that were really smart that we've gotten away from us. We have to remember why they work and how we can bring that stuff back into what we're doing. Essentially, this graphic captures the wetting and the drying forces and phenomena which occur with our buildings, most of the things are caught here. The colored vector arrows give us representations of those moisture loads. We do have a pressure difference on the air pressure difference we're showing. And bear in mind that air pressure difference is a driving force for moisture as well, because air has moisture in it. So air movement has moisture moving at the same time. Temperature difference is also a driving force. And so we've got water coming in and we're going to have to get it back out. So we have to take advantage of the forces at our disposal to move that moisture. And essentially, these are the forces that we do get. That little yellow orb in the top right corner is our friend, and we are going to try to use it along with the wind to our maximum advantage here, because the forces from nature don't have to be necessarily our enemy in this regard. They can actually be our friend and help us get back into a dry place. Now, this is a map of the U.S. climate zones from the Department of Energy. It shows our 8 temperature climate zones, and these are based really upon heating and cooling degree days as found in ASHRAE, and that's not changed too much. We've got climate zones 1 through 8, 1 down on the tip of Florida and 8 up in Alaska. What's really important for this discussion about draining and drying, though, is whether or not you are in zone A, moist, which is pretty much east of the Rocky Mountains, B, dry, which is west of the Rocky Mountains, except for zone 4C, marine, which is right on the Pacific coast and has a weather which is truly dominated by the ocean currents and the ocean temperatures. For the most part, our weather years are influenced, traditionally have been influenced by the position of the jet stream and by ocean water temperatures. Those gave us the El Niños and La Niñas, and of course, the actual jet stream was giving us your polar vortexes and the actual positioning of where the weather fronts were, and when we had Canada's cold weather and when we got the Gulf of Mexico's wet weather, right? So that's what, for the most part, has been driving the weather across the United States. And now we include global warming and the impacts we're currently measuring on everything from temperatures to rain depositions, individual storms. I guess you guys have all noticed that the 1,000-year storm tends to happen every year now. And so we're quickly coming to realize that things like the plumbing code and other things that we're basing our calculations on how to handle moisture might need to be either looked at, changed, or we immediately start putting in a bigger fudge factor or safety factor in our calculations to accommodate more rain coming in shorter periods of time. And because that's going to influence, how we get the water off the building, which is all, of course, found in a plumbing code. And that is a really important goal: get the water off the building, because the longer the water sticks around in contact with the building, it's going to get in. It's going to get in. When water sticks to stuff, which it does, it finds its way in. And we'll talk about how that occurs, but the trick is to get it off. Now, how much water is going to land on your building is really influenced by the total rainfall, the wind-driven rain, and of course, that surrounding topography. This is a map of the annual precipitation in the United States between 1961 and 1990. What's interesting as of late, if we look at the really hot zones up in the Pacific Northwest, they've been replaced by the mountainous Carolinas. The far western North Carolina around Greenville has dethroned the Pacific Northwest for the most amount of rain, which occurs in a year. And so, kind of reset ourselves with the way we think about the weather and start to come to grips with the fact that some of these rainfalls are going to be a lot bigger than they have been in the past, and we're going to have to deal with that moisture. Now, how much moisture gets deposited on your building, because the rain doesn't fall necessarily straight down. Usually there's a component of wind involved. And so we have rain traveling at an angle. And the wind-driven rain deposits the water on the side of the building as well as on the roof. And here is a photograph and a CFD model to show you rain deposition differences between a big blockish commercial building and a low-rise residential building with different kinds of pitches on the roof. On the right, if you look at that inverted horseshoe which occurs, that's also how wind strikes the building. Where rain shows up first is where wind strikes a building, because as the wind skirts around the building or tries to go around the building, the rain's got momentum and keeps on moving and slams into it. So you can kind of see how wind hits buildings by watching them after the rain first starts. And in that high rise there, we see that inverted horseshoe where it's the biggest at the top and at the corners. And within about half an hour, it all runs down the building and you can't see it, that horseshoe anymore, but that's still typically where the wind-driven rain is occurring. Now on a home, that's harder to see. So here we're using an example from something that's called CFD modeling. Computational flow dynamics is used for the modeling of air flows or for fluid flows. Here we're modeling rain deposition from wind on a residential structure. Look at your soffits, look at that low slope roof, look at the edges of that roof. This is where residential buildings take a true beating from wind-driven rain, is in these corners. This is where it really shows up and where you really have to be mindful of what's happening to that moisture. Where are you storing it? Where are you getting rid of it? Again, the longer that moisture sticks around in contact with the building, the greater the chances it's going to get in. That being said, look at things we do today and just scratch your head and say, what are we thinking? Why aren't we doing what our fathers and our grandfathers did? If we look at our houses, you know, the picture in the top right there is actually from a real estate listing in Baton Rouge, Louisiana. When you live with the sun on your head and torrential amounts of rain, you learn to have really big soffits. Look at the shadows on that wall. Right? Half of those walls never even see sun or see rain because of the overhang on that roof, right? That's something we seem to have lost sight of. We like to get rid of soffits. We have really, really small soffits on a lot of our new homes, and it really works against us in a lot of ways. If we look at the top left picture here, we have a typical, you know, gable end wall here. Lord help us, this is the wind-driven rain direction. Now, by the way, you can find the wind-driven rain direction for any zip code in the United States from free weather generators available online. One of my favorite places to look for free tools in this regard is Oak Ridge National Laboratory's website, ornl.gov. And at that site, you will find free weather rosette generators, and it will show you both the wind-driven rain, the wind-driven snow, the principal rain direction, any kind of weather you're looking for any zip code in America. And when you look that up, please don't point these gable ends into that wind-driven rain if you can at all help yourself. And if you can't help yourself, let's get on a landscaping program and do like the picture in the bottom and learn to put up trees in the direction of the principal wind-driven weather, because we learned a long time ago that trees are our friends in this regard. So there are things that we can do both to help ourselves or to make things more difficult for ourselves with regards to how the rain is striking our buildings and being deposited on our buildings. The goal is to get as little water on our buildings as possible, and the water gets on to get them off as quickly as possible, because it comes down to this whole idea of drying. How do we dry once the water gets on? Well, for the most part, what it takes to get moisture off of something is energy. Water is really, really sticky stuff, and it wants to stay stuck to the things that it is on. And so to get water off, you typically need energy. If the energy used to come from inside the building, because we had very, very little insulation, if we had a wet wall, it wasn't a big deal. We could push all the energy through it and dry it right out, move the moisture with the energy. And that is typically the direction that the energy is going to, the moisture is going to flow. It's going to flow in the direction of the energy flow, or think of it as your heat flow. What we see in this case here is solar energy. Where is the most amount of solar energy? The sun can be your friend, and you can take advantage of solar energy, but if you're going to push the water out into the outdoor environment, you need a dry sponge. You need dry air. Now, the air doesn't have to be bone dry. It's just got to be drier than the surface you're sitting in. It's got to have a lower vapor pressure. Now, in physics, we deal in actual humidity, not relative humidity. Actual humidity is actual vapor pressures. It's a much easier way to look at things and understand which way that water is going to flow. Relative humidity is going to throw you off, because you're going to say, hey, wait a minute, in the wintertime outside, it's 80% relative humidity. And inside my home, it's 35% relative humidity. So why is the moisture flowing from inside to out? Well, because the actual humidity, that 80% outside, is a very, very low vapor pressure. It just sounds high because it's so cold out. When we look at this map, this is relative humidity. Just remember that you just can't be solid blue in order for this whole concept to work. If you've got any room in the air to put some moisture, then you can move the moisture into that air. That can become your sponge. Now, that being said, the drier your sponge, the better off you're going to be. It's just, we all know this organically, that if we have a really dry towel, it's going to soak up a lot of moisture a lot more quickly than a wet towel is going to do that for us. But remember, a wet towel can still suck up moisture for you. The trick is to keep bringing in more wet towel before that wet towel gets saturated. We're going to talk a little bit that coming up. Again, when we talk about the science of drying, we're talking about sun and energy from the sun. Here's a map of incident global solar radiation on the US. You know, it is scary that parts of Western New York are as bad as the Pacific Northwest when it comes to the amount of energy you're going to get from the sun. But that being said, you can still use it. It's still going to work for you because we're not just going to use the sun's energy. We're also going to use the energy of the wind to run a dryer for us and help promote drying in our residential claddings. The whole idea is getting water from the far left of the scale all the way to the right end of this scale. You know, what moves it from the left end to the right end is energy. And what takes you from the right end to the left end is taking out energy. And that's the only difference here between these forms of moisture that we have before us. But, you know, the further to the left you are, the more energy it's going to take to get you to the right. You know, but anywhere in between, you can get moisture over to that right and get rid of it as long as you have some place to put it. Now, we're talking about trying to dry to the outside. So what we need is air that's at below 100% RH. Clearly, if it's at 20% RH, it's got more capacity than 100% RH. Why is that? It's this whole concept of dew point that, you know, you've been lecturing you guys about since you were in design school. The idea that the air, as it warms up, it can hold more moisture. The dew point is a temperature at which if the air cools off 1 more degree, it's going to have to give up its moisture. It can't hold anymore. We're going the other way. We're saying we're going anti-dew point. We're going to say, well, we're going to bring in lower humidity. So we have a greater capacity to take this moisture with us. All we need is a few degrees difference and a little bit of relative humidity difference, and we can take that moisture with us. The more, the better, the more, the faster it's going to happen. But don't get turned off thinking that in Westchester or in southeastern New York or in Connecticut or in New Jersey or in northeastern Pennsylvania that it doesn't work. It absolutely does work. It works in every single climate. Now, the things about water. Water flows downhill, right? The Romans knew this. We know this. The problem is it's really sticky stuff. And if it's in contact with something, it's going to want to flow in any crevice, any void, any capillary it can find to get back that surface. It doesn't have to flow downhill when it gets to that crack. It can flow back a flat, route. It can actually flow uphill, right? Through surface tension and through airflow. You've all seen the water meniscus rise on the side of a piece of glass or the glass, your drinking glass. That's the surface tension of water walking it up the side against gravity. So the water is going to try to walk itself back into that building. The whole trick is to get it down and off the building as fast as possible. Try not to have voids. Try not to reverse lap stuff. Try to give it a way out so that it doesn't try to find its own way in. It will take the path of least resistance. Just give it one, and it will typically go that way. Now, when air flows, moisture does flow with it. It's because moisture is in that air. That's the whole magic. You're just dealing with a fear of moisture in the air, that all of a sudden the air is going to be coming around some surface that is too cool for it. It helps to cool it off. It cools it off quickly enough that the air reaches its dew point, and then it cools off just a little bit more. Then all of a sudden that surface, that cold surface, starts to sweat, right? It's your glass of iced tea in the summertime. It's why in life, things that are colder than the air around them tend to be wet, and things that are warmer than the air around them tend to be dry. It's this whole concept here of that air's got moisture in it. And so you don't want it flowing up against cold stuff, because at some temperatures, it only takes a little bit of difference at some humidities and bang, all of a sudden you're sweating. So you want to be careful about these airflows through your assemblies. Airflow is a friend, right? That's why we blow air through our dryers when we're drying our clothing, because we need that fresh air and the lower humidity. And so we want the airflow coming through, because if the air just sits still, it's going to get saturated. And once it's saturated 100% RH, it can't hold anymore. So we got to move it out before it gets saturated. That's why in our dryer, we flush it back out. We bring in some fresh air from the house, and that air has some more capacity. But that's the danger and the benefit of airflow, depending on how you're using it. Usually when we talk about airflow and the need for air barriers and things like that, this is what the graphic you'll see it probably 100 times in your career, and no one will tell you where it came from. It actually came from a book called Building Science for a Cold Climate by Rick Quirette, NRC Canada, I think like the 1960s or 70s. It's such an old graphic. It's been around forever, but it captures this issue of how much moisture can flow and how careful that we have to be in this regard. Sorry, I'm trying to move a sunscreen here. Moisture also flows through capillary suction. I mentioned this already. If the moisture is flowing down that building and it gets to a capillary, it will get pulled back into that material. Capillaries exist in things that grow. Capillaries exist in things that cure, not under heat and pressure. So we'll find capillary in a lot of the building materials that we use, especially our exterior materials. If they're not things like, say, a synthetic or a polymer siding, well, most organic sidings all have capillaries, so they love transporting stuff. Wood-based sheathings are full of capillaries. They love transporting moisture. Gypsum, that's got capillaries. Well, actually, no, it's got voids, but it will travel in other ways to the gypsum. But this capillary motion is something you really got to be careful about. We usually break them with voids, with gaps. It's the best thing to do, to create like a drainage system behind some brick facade. It's very, very effective. The other way you can do it is you can cast a hydrophobic layer in there. Some material is going to repel water. If you think you got capillaries on either side, that's another way to get in there. But the most common thing that we do is to try to create a bridge, right? Something that the water can't get across. Like for a brick cavity wall, we create that space between the brick and the next layer so that water can't necessarily jump across it. What's interesting is some research that Dr. John Straub did up at the University of Waterloo that showed how much actually blows across that cavity onto the next surface because of some of the voids that are in there. But that's maybe a discussion for another day. So airflow, it's a reaction to pressure. It is going to find a place of lowest pressure. That's basically what nature does. The things that move are going to be the stack effect, the flue or the ventilation effect, the wind or the system. And there's examples for each one. I don't want to go into it too long with you, but we're going to take advantage of that wind effect. The fact that when the wind blows across our building, it creates both positive and negative pressures. It's the negative pressures that typically are the ones that are going to pull air out. Nature abhors a vacuum. When you create a negative pressure, air is going to push its way in from somewhere else to get in there and fill that void. So if you can create a negative pressure by going across a roof at the ridge, you're going to create a vacuum underneath that ridge. And therefore, the air is going to try to push its way up to that vacuum, and that creates your whole roof ventilation scheme. When the air blows around the corner, the same thing happens on the corner of your building. That's why we create compartmentalized rain screens on really big rain screen commercial jobs, because actually going around the corner sometimes it can get really funky having positive and negative so close. So we'll try to compartmentalize them to not have them also occurring inside the actual rain screen. But that wind effect is really, really powerful. That's the effect that lifts a jet plane off the ground. I mean, you can't deny that force. It's extremely effective, and it's free. And so we're going to take advantage of that in our attempts to try to put some forces to play to help us dry out our buildings. The thing with this airflow, as I pointed out before, is that if it flows up against a cold surface, what we see is all kinds of trouble. Here's a chart that shows the dew point at different temperatures and humidities. And what we see is that if we take air at 75 degrees on your left-hand y-axis at 35% humidity, your top x-axis there, that means they're going to condense at 45 degrees. So that's the concept of dew point. The thing where it becomes really, really tricky is go back that x-axis closer and closer to the y and see how close those temperatures get to the actual air temperature. As you start getting to 90 and 95% relative humidity, you can't take a drop in temperature. You are going to sweat if you do. And that really is the big danger about the dew points that people are always warning us about to stay away from, is that it's really, really tricky. We try to prevent these vapor pressures from ever getting so close. Now, when things do get wet, how they dry is really interesting. The concept of evaporation airflow does help us quite a bit. Evaporation is driven by a bunch of different parameters: the surface area exposed, the surface temperature, because the closer you are to the excitement temperature, the less energy it's going to take to get that water off of there. The colder the temperature, the more energy it's going to take to get up there and get that energy going, to get that excitement to break free. Air movement does give us some energy for this excitement, but the biggest thing about the air movement is, again, remember what happens when your towel gets saturated, all the drying stops. The air movement brings us a fresh towel, and even if it's a little wet, that's okay, because it's still got some drying capacity. As long as the air movement keeps on occurring, we keep getting fresh towel, we keep getting drying capacity. And that's why the air movement is so important to us. Heat flow is one of our final things that we're going to talk about here in terms of these forces. It typically flows through conduction, convection, or radiation. Conduction is materials in contact. We don't get too much of that in this example because R value works against you. R value is resistance to conduction. And so when we slapped all this R value into buildings, well, that's how to get rid of the energy force. That's all of a sudden why we started getting wet and staying wet. Convection is the motion of a fluid or a gas. Just like it is for drying, is the same thing for energy. By bringing you a fresh source, either hotter or colder than the original surface, it will help keep transferring that energy. The final one is radiation. This is what we're going to take advantage of in our examples today. We're taking advantage of the radiation of the sun. It's extremely powerful. It is energy passed between bodies of mass at different temperatures, and it goes right across the vacuum of space. You've hated it when you're wearing a black t-shirt on a hot sunny day, and you've learned to put on a white t-shirt for that reason. But what we're going to do is we're going to take that energy that occurred to you when you were wearing that t-shirt, and we're going to make that energy run a dryer for us. It's our best friend. Not only are we helping to dry our building out, we're managing the energy flows. We're warming up our surfaces. Guess what? In the wintertime, when your outer wall gets really warm and your inner home is really close to that same temperature, energy flow about stops across the assembly. This is the magic of passive solar, right? When you can get your outer surface the same temperature as the inside of your home, there is no energy flow across it. So if your outer building is getting warm in the sunlight in the winter, you've got very, very low energy flow through conductivity through that assembly. So warming up these outer surfaces and taking advantage, this not only runs a dryer for you while that's occurring in the wintertime, you've got like no heat loss through that wall. It's not happening. The idea I touched on initially, you may have seen in the flyer that went out, is that all materials have this idea of moisture storage. Stuff gets wet. Things have always gotten wet. Some stuff gets wet and doesn't mind at all. Everything else, though, has some kind of limit. You've typically got to stay within. Now, these are the safe moisture storage limits for a lot of common materials that we use in our buildings, in the framing, in the insulation, or of the exterior. We have some interior gypsum board mentioned there at the bottom. The concept that any one of these materials can get wet is absolutely true. How long they can stay wet is kind of a separate conversation. You will get above certain moisture limits. You're going to get a swelling that occurs. You get capillary saturation. You get cellular saturation. You can get biological growth, contamination, mold, and mildew can occur when water becomes available at surfaces because of
any of this. Oracle.
So there are some limits below these safe moisture storages that you're going to want to stay below for biological contamination reasons. These are really up there what something can live with regards to how much it is going to absolutely absorb. You'll see fiberglass down there says 0. Fiberglass won't absorb any moisture. It will adsorb moisture. And let's not get confused between adsorb and absorb. You probably promised yourself you never need to know the difference. No, adsorb is on the surface. Glass adsorbs water. Wood absorbs moisture as well. Not only does it stick to the surface, it will actually go into the cellular structure of the material. And that's really important. When materials get absorbed into the cellular structure of material, you need so much energy to get them out before you're in trouble that you're pretty much in trouble. That a lot of the energy that we would use to do this in the manufacturing of these products has been done in ovens. Lumber gets kiln dried. Gypsum boards get dried through ovens and things like that help do all that for us. Once a piece of lumber gets up to a certain moisture storage limit, over, say, like for a piece of dimensional frame like a stud, once you go above like 19% moisture, it's simply going to be growing mold, because you can't dry it out fast enough unless you throw it into an oven. It's just not going to happen fast enough in nature. So again, these are just the safe moisture storage limits with regards to stuff not swelling, falling apart, getting fungus on it. Fungus is a higher level of moisture, which actually will consume the substrate and cause you structural damage. Mold doesn't cause structural damage. Fungus does. Fungus is at a higher limit. But all these limits I'm throwing up here is that how much a material will actually absorb. There's some level below here you are going to need to stay. Here's a graphic kind of catching our big drives again. On our left is what gets us wet. Right? One is the rain. Number two is diffusion of moisture from the atmosphere in there. Number three is going to be airflow. Number four is going to be ground moisture. On the right is our forces that drive us, that dry us. Number one is evaporation off the surface. Number two is diffusion. Number three is gravity. And number four is the one I really want us to focus on and what we're learning today. It's airflow. It's evaporation. This is what we want to try to bring in back to our buildings everywhere we possibly can, because it does amazing things for us when we can do that. When we do that, we can take all of those moisture sources and we can stay below that safe moisture storage capacity for the entire assembly. Because what we're doing is we're making that bottom right spigot bigger than it ever was before. And we're going to make it there every time the sun comes out and every time the wind blows. There are very few assemblies in which this does actually hurt us. In most assemblies, this does help us. Computer modeling will confirm one or the other, but I'm going to show you some examples of how it actually works and how it actually does help us. Now, one of the things that's really important into this discussion that we've had thus far is that draining and ventilation rate. How much airflow? I can tell you your home dryer runs at 200 to 300 cubic feet per minute. We're not going to do that. We don't have that great big fan motor running. We only have the sun and the wind, but we can get pretty close. The question becomes, what is it? What is that number? How is it? Now, there's really amazing computer modeling and simulation tools out there. I use a program called WUFI, W-U-F-I. It's a free software you can download from the U.S. government, from Oak Ridge National Laboratory. And it allows you to actually put ventilation rates behind claddings. You can put leaks inside walls. And you can put ventilation rates inside claddings. You can do all kinds of really cool stuff. What is really dangerous, and you should never do it unless you actually know what is the ventilation rate. You're playing with fire if you're just throwing numbers in there without knowing what they really do. It's like any simulation software. An error this big going in is that big coming out. And so you really want to know what those numbers are before you start introducing them into a calculation. Well, this software functionality has been in WUFI for at least 10 years, but mostly people were playing with the numbers because unless they can measure it empirically on a small scale for an individual assembly what their ventilation rate was, we didn't really know what ventilation rates were behind claddings. We knew it was supposed to be there. We knew that the code thought we were doing it. It's actually in the code commentary from like the early 2000s that they thought all walls were draining, drying, and ventilating. And you're like, what? They didn't realize that we weren't hanging claddings over furring strips in air spaces. They thought we really were. They really want us to be doing that today. It's actually in the code language. You can find language in there for cladding ventilation rates and the removal of needs for vapor retarders if you're actually ventilating your cladding to a certain rate, because what they're going to show you is that if you're ventilating your cladding to a certain rate, you can accommodate some wetting. It's really a bizarre concept. But yeah, the code's going to say, yeah, what? We're going to actually let you do something that lets the wall get wet intentionally because we know you're also doing something which is going to dry it out before you get into trouble. And it comes from this. But the question in the past was like, well, how much ventilation do we really need? Well, the code's telling you that now, and it's coming from this research. The research came from these lunatics over at the University of Leuven in Belgium. And these grad students had gone out and measured ventilation rates behind all different kinds of claddings to find out how did different claddings breathe, how much air change per hour, that's ACH, how many air changes per hour in that volume, and what sort of things influence that air change per hour in the construction and the design. What they found was that, and I'm going to just be using North American examples here, and these measurements were made in North America. In red brick walls, if we just weep the wall, right? If we do everything else right, if we put up an air resistant, water resistant barrier on the other side of that cavity that's completely airtight, and we just put a weep at the bottom of the wall, and we put that weep about every 3 meters, that's pretty far. What we're getting is around 1 ACH per hour, 1 air change per hour. That's all you're really going to get in that cavity if you actually weep that wall and the weep is open, right? That means you guaranteed it was open. If you chose a material other than a weep tube that you had a better chance of staying open, like a product that was like a corrugated vent that you might see poked vertically in between two bricks for a drainage medium, and I don't want to mention any product names, but those corrugated continuous pieces that are going to be a whole brick height are a lot more open and will get you as much as 10 air changes per hour. And that's pretty good, but that's a really big difference. That's a 10-fold difference in our walls. And that one is only occurring if your wall is actually open. I promise you, a lot of our walls aren't actually open. And if all the tubes are open, it's a miracle. So we got to start counting out, assuming a whole bunch of those tubes aren't open, and roll back our expectation about how much that wall is actually ventilating if we're going to put that number into a model. What they measure on sidings is really, really interesting. This is great news for our siding applications. And one of the reasons they are so durable, there's a lot of ways you can do them. You can have things like vinyl sidings that are loose nailed and inherently ventilated because they are loose nailed and they have drainage holes within them. You can take lap sidings and install them over furring strips or over other materials that will guarantee a clear airspace for drainage and ventilation. If that clear airspace is now open at the bottom and the top, that's a big change over the brick wall. I didn't tell you on the brick wall. That brick wall was not open at the top because we don't open brick walls at the top as a matter of habit. We tend to seal them off. Even in residential constructions, we tend to seal them off at the top of the wall. We put a fascia board down and we caulk below it, and that whole thing is just totally sealed off to the outside. It is not open to the inside. And we're not allowed to vent that up into our soffit ventilation. That better not be venting up into our soffit and up into our attic ventilation. That's supposed to be compartmentalized off of there. So right now, that's just a big, dumb, dead thing at the top of the head. However, in our sidings, because they are loose, and if we are putting them over a furring strip, and if we leave them loose at the top, like at the picture on the right, they measured everywhere between 100 and 1,000 air changes per hour on our walls that we built that way. Now, these weren't 40-year-old walls that have been painted 20 times or even 10 times and sealed off all of that. They weren't ones that the homeowner came back and caulked up and sealed off on us. These are walls that were left open by design, as they always were. When we used things like penetrating stains, we never had a problem with sealing these things off. When we started coating them with continuous coatings, we started sealing them off and they started performing completely different for us. They started cupping on us and doing all kinds of things that surprised us. But it's because we changed the way that those materials were breathing and the way they were drying. The more you leave that cavity open, the bigger the impact. I'm about to drop the impact on you here for a brick wall in Albany. I ran the simulation yesterday. If I take a brick wall in Albany, this is a 2x6 wall. If you look at by the way, this is a screenshot from WUFI, W-U-F-I, the moisture simulation program that I was using to look at this issue. If you look at the materials on the left, the screen, the left column shows the constituent materials in the construction. What we have here is basically a red brick wall built over an air layer with a spun bonded polyolefin weather resistant barrier. You may know that a material that has a trade name of house wrap on it somewhere. It's one of the most common building wraps we put on our residential constructions today. That's just over OSB sheathing and then over insulation with a vapor retarder in it. The picture on the right is the exact same model. The only difference between these two is a cladding ventilation rate. I have put on this wall a 1% window leak. Now, this wall built with no window leak, and may you always be that way, is not a problem. And you know that. You built this wall in your own neighborhoods, and it's not been a problem for you. But if we got a window leak, or someone reverse lapped our weather resistant barrier, or something happened over time, all of a sudden water got back there. This is kind of what's difference between these two models. In these two models, it's assuming that I've got a 1% wind-driven rain window leak. It probably could happen at some point in time when caulking isn't maintained or something else. I'm letting that water drop down now onto the top of my sheathing in that saddle of the rough opening. I'm letting that front of that get wet and to see what happens. On the left is what happens over the course of 3 years. Look at the right-hand Y-axis. For manufactured wood products, 23% is the safe moisture storage limit. Above 23%, they start to swell, which means if you're using it for nailing for all those brick ties, it's got to come out. If you're using it for racking resistance for the 2x6 framing, it's got to come out. When OSB or plywood swells by 15%, by APA guidelines, it's got to be removed because it can no longer be trusted for its structural properties. That's really scary. On the right, what we see is that with that ventilation rate in place, I gave that a 1% window leak with a 100% ACH on a brick wall, not a sided wall, on a brick wall. How did I get that? By leaving the head open, and we can talk about details, but all I did was leave the head open. I left the detail, I let the fascia board free of it, clear of it, let the caulk space open, let the air get around the top of the brick, and all of a sudden, bang, the moisture is gone. Every year, even with the window leak, that wall cannot gain moisture because every time the wind blows, every time the sun comes out, it runs a dryer force and it gets rid of the problem. So what have we learned? I know I'm going fast, but I know you guys are on a schedule and I'm going to get you there. We've covered a lot of stuff. I know, I promise, but if you take this same information that draining and drying is good, right? Getting the water off our wall from the very start is the best thing we can do. Keep it off a wall, get away from our wall as fast as possible, and we have a better chance of surviving. But when the wind and rain gets the water onto our walls, what can we do to facilitate the drying? Remember, the wind put it there, the wind can take it away as well. We look at our different lap sidings, we realize that installing them over air spaces is critical to their performance. When we nail the head of that lap siding hard against, or we do ship lap nailed hard against that weather resistant barrier, it's water resistant barrier, right? It's not weather, they don't promise it against UV. It's water resistant barrier is not going to do well for you if it can't actually drain the moisture away. You're going to be holding it against your product and holding it against all the materials, and it is eventually going to be a problem. If you let it drain and dry down and away, it works amazingly well. So pick systems that can do that. Pick materials that can do that. Look for ways to get that done. The only material I said I was involved in a telephone conference years and years ago, long before I ever joined Saint-Gobain, with the building code about this concept of draining, drying, and what sidings they thought were nailed on top of furring strips. The only siding in America that they thought didn't have to be nailed over furring strips was vinyl siding, because it's loose nailed. And it makes perfect sense when you look at the research. You say, oh yeah, this is why it works. This is why when you tear apart a home that's got moisture problems and you do a total facade tear up, you find the brick or the masonry's got the moisture problems behind it, no matter what the orientation was, and the darn vinyl sided wall's got almost nothing, no matter what the vinyl orientation was, because of that loose nailness of it. It inherently drains and dries. Otherwise, when we look at our sidings, we're going to want to make sure that we're getting over some kind of medium that is going to allow them to drain or dry. When we build our claddings, right, there's a picture of on the right of how to do that brick wall and leave that cavity venting. We don't let it vent up into that soffit. That is not allowed. We do not put extra moisture. That's like venting our bathroom or our dryer up into the attic. Please, please don't do that. You're not allowed to do that. The designs, the calculations we have for roof ventilation are really tenuous today to begin with because of how much insulation we're putting in our homes. It was a lot safer with less insulation. Now with more insulation up there, the temperatures are much closer. We need all that ventilation. We can't take any more moisture up there. So don't vent up in that way. You can't handle it. So make sure you're venting it to the outside. And when you do this, make sure the homeowner knows, oh yeah, by the way, on this page right here in the homeowner's manual, you signed on this page that you would not caulk that joint 10 years from now when you decide to paint that fascia board again. Don't caulk that joint. If in doubt, put something in there so they don't. Put in, some bug screen or some bird mesh or something else that makes it clear to them that this thing is meant to be right where it is. When you look at your stucco and look at your EIFS, remember they can be installed like drainage systems. but it's stucco system with the stones in front. And so you don't really like to put those expansion joints or all the water managed things about stucco in this system. But pay attention, that is a stucco system. And so you're at a pickle there. So if you really have a client or an assembly where you really want that look, go for these new systems that have the stone hanging on a siding system. These can be installed as a water managed system. On the left is your synthetic stone system in the traditional application in stucco. On the right is a newer synthetic stone system that uses a metal grid pattern to hang itself on. It hangs like normal siding. So here you're going to get that same stone look, but an actual water managed system that never gets caulked. You'd pretty much have to shove your sandwich back there to screw it up. It's a really, really bulletproof system. And there's a couple different manufacturers of these kind of products out there. Look for ones that, again, are going to hang in accordance with what you're doing and work with what you got going on. But when you do, you've got the water managed system that you're looking for with that look of stone. And so again, for no matter what the residential cladding you are putting up, look for a way to do that as a water managed system. If you do, we can get all of these things. So in summary, we have talked about that's trying to create this boundary for us, but the pickle we get into is that energy was our friend. Energy is what kept us dry because we've never made a dry building in our lives. And so we have to find a way to put energy back into the equation, get the free energy we're allowed to, which is the energy of the environment, and put into our assemblies to run that dryer for us. And again, the sun is great and the wind is great, but just the wind will work. Just the north, the west, it does. The sun can be over on the east in the morning, and you can still run a dryer on the west and the north when the wind is blowing. And so these things work for you almost year round. It's a tremendous benefit, and it's the kind of thing that we need to put back into our repertoire of solutions, because I'm afraid that they're going to keep telling us we have to put more layers in this wall, which is not going to make things easier. But if we can dry from the point moisture gets to and put it back out again and not let it get inwards, then we're just inherently in a better place. And so that's how all of that works for us. That's why some systems are so much more durable and bulletproof than others, and some we just can't seem to get our own way with. It's all right here. This is some of the secrets. And so I really, really urge you to take a look at this idea, and I'd be happy to share with you any of the outside research and places you want to go if you want to learn more about the computer modeling and where you can download more of that. And again, the software is a free software you can download from Oak Ridge National Laboratory. But a lot of this research is from different universities and things around the world. It's really, really cool stuff, and it really works. You'll see demonstration projects going on with this kind of stuff from Building America to everyone. You know, it's why I mentioned that if you actually look out in Pacific Zone 4C Marine, the Pacific Northwest, this has already shown up in their code language under ventilated cladding assemblies. It's letting you get rid of the vapor charter in the Pacific Northwest because it's saying, yeah, we know it's okay to get wet on your sheeting in the winter because it's too cold to grow mold. And by the time it gets warm enough to grow mold again, we're going to dry out so fast, it won't have a chance to grow. And they've been doing that as experiments out there and showed it's worked for them, which is why they put this language in the code for them and got it out there, because it gives them a little more design flexibility, ways to not be putting more materials into the wall if they don't need it, and ways to use the forces of nature rather than the forces of the fan or the furnace to keep us where we are safe and where we are dry. So that was all I had. If we have any questions, I will stop sharing my screen again.
Excellent. Thank you for a wonderful presentation, Lucas. And yep, folks, if you want to put your questions into the chat, we'll have Lucas address them. Looks like the first one is, can any siding be installed as a ventilated cladding?
Yeah, absolutely. Except for the ones where you get into a pickle, stucco drains, but it doesn't really ventilate because it's not usually open at the top. You can put stucco out over in airspace. You will find some details for it. It really requires using something like a paper-backed lath that's been furred out from the wall. I've seen this assembly done, and I've seen a group called the Pacific Northwest Plasterers Bureau actually publish some details for it back about 20 years ago, when that became their go-to bomb-proof assembly for doing stucco in Seattle. Well, other than that, though, you think about any rigid siding, vinyl needs to be stuck on top of something. It can't be hung on top of two furring strips, right? So there we say the stucco's okay, the vinyl's okay because it's loose nailed anyway. Everything else that's rigid, you can pretty much get out there over those furring strips. That's about the best way to go it. And the problem with furring strips becomes, it's pressure treated. I need to be using galvanized or stainless steel. What's happening here? I can't be putting galvanized on here. What should I be using? Do I have to go to stainless steel? The answer there is, I don't think you do. And Dr. Joe Stiebrook up at the Building Science Corporation up in Massachusetts, look for his research, which is free online. Building Science Corporation's amazing about publishing their stuff for free. Find the stuff where he's talked about it, because he did his own home as a drainage plane like that, and he tore it off to look at it. And what they had done was they had used some galvanized and some stainless, and what they found was that the galvanized wasn't wet long enough out there to cause any issues whatsoever for him. But look at his research if you have that question. Other kinds of materials, if you're going to do using that to put them out there and over in airspace, make sure that the material maintains that airspace for you, that it doesn't get collapsed or crushed by the installation of your siding.
Excellent. Hey, how much of a space is needed to drain and ventilate it?
I might have dropped his name already. Dr. John Straub, Straube, University of Waterloo up in Ontario. Dr. Straub did a whole series of experiments on draining and drying of assemblies and wind-driven rains. How much water gets into a cavity was a question we always had. Dr. Straub's measurements on brick cavity walls specifically found that 10% of the wind-driven rain got back in that cavity. How much of the rain drained out? Half. If you had a minimum 3/8 inch wide cavity, there's your answer you're looking for, Ron, is 3/8 of an inch. That drained the exact same amount of water as a 2-inch cavity did, which was only half. The other half of the water never came out. It just stuck to either side. It stuck to the stuff it touched. Gravity wasn't strong enough to pull it out of that cavity. What Dr. Straub found was that if he opened the top of that cavity, whoosh, it was gone. Oh, we're getting back to the story again. But it was 3/8 of an inch. It all came around. But 3/8 of an inch is what your minimum needs to be. Products that will give you less than 3/8 of an inch will still give you some drainage. And if they're open at the top and you have actual airflow, you will get the drying, because that air will take out the stuff that's going to stick around. But a lot more is going to stick around at 3/8 of an inch than would ever stick around at obviously a 1/2 inch or 2 inches.
Excellent. All right. One of the illustrations showed soffit vents. However, Patty thought that you recommended to not vent into the soffits. So please clarify.
Well, we have the ventilated attic is still we have the code allows us to do a vented attic and a non-vented attic. When we vent our attic, we have several different ways we can do it. As a person who spent his whole life cutting up buildings, I want to get airflow on as much of the surface I want to dry as possible. And that is one of the benefits of venting a soffit versus venting from a gable end, that I can maximize the distance that the air flows on the underside of the roof deck. And to be honest, there's only two kinds of roofs, ones that are leaking and ones that are going to leak. Eventually, every shingle or every roofing material is going to wear out, and we're going to get some water onto our decking underneath. And having that airflow really gives me the evaporative potential that prevents damage from occurring before I can replace my roof or catch the problem. And so we do like soffit ventilation for that reason. We just don't want to vent the cavity up into that soffit. So we want to get it out and around. So in that installation, we might be looking for a different kind of solution or a different way to go about it. We might be doing some other kind of way. But yeah, no, your observation is absolutely correct. If we do have soffit vents, we don't want to vent up into the soffit. For roofing, we want to vent the attic, and we love the soffit vent for that reason. But in this assembly, we have to be careful about not putting that moisture up into that attic for that same reason. As I mentioned before, the attic ventilation clauses we actually got from like the 1930s, and it happened when we first started insulating attics, and we sweated them all out. And then we said, 1 to 300 ratio. And all of a sudden the problem went away. And then all of a sudden in the 1970s, we started doing it again, because we started adding more insulation. And then we started sweating our attics again. They said, 1 to 150. And that's our new thing, right? Now we try to do 1 to 150. But that was before we started putting R100 up in our attics, like is up in mine. And now you need even more because now your surfaces are even colder than they ever were before. As I said, if you can be warm around cold air, you got no problem. When you're cold around warm air, you got a big problem. And so we really like to keep stuff, the colder we get it, the more problems we get. So we need more airflow to help us with these higher levels of insulation.
Sorry about that. We just muted that person, and there we go. All right, and let's see. Next question: where can we learn more about computer modeling of moisture?
So the program I like to use, and it's perhaps the most used program in the world, is called WUFI, WUFI. You can just type that into any search engine, and you're going to get to a WUFI North America or WUFI America page. You also get to a WUFI European page because it's originally from the Fraunhofer Institute in Germany. Go to the American page, the English page. It's a lot easier to understand, but it's going to get into all the different stuff about the program. As I said, you can download a free copy from Oak Ridge National Laboratory's website. You've already paid for it with your tax dollars. So get into it. You can start learning it from there. Then if you want to get into it real hard, there are seminars and courses that travel around that teach it. And you can even get into advanced WUFI modeling and things like that. I run it every day. If you want to get into it and you have questions, I'm more than happy to work with you on it and help you out and help you learn your way through it and help you get to some resources and some backup information. It's a tremendously insightful tool, but it's also scary because it's like any simulation software. If you don't have confidence in it, it's good to learn so you can understand what someone is showing you. But if you don't have confidence, you're not going to want to stick your toe in there. Let someone else do it, and then you'll have a better way of understanding what they're doing because you know what it is they're doing.
Outstanding. Excellent. Folks, any last questions, please put your question into the chat function. I see Michelle has put the WUFI link into the chat, so if anybody needs that, please grab it. It's right in the chat function. And again, you want to put in your contact info there, Lucas, or put it up on the screen or whatever's easiest?
I will try.
And then Mr. Murphy, we're at 5:15. Did you want to wrap it up and thank our sponsors, or did you want me to do that, sir?
Thank you very much, Ron. Thank you, Earthkind Energy, Bright Energy Wellness. We thank you, Certainty, to Michelle, and most of all, Lucas Hamilton. Thank you so much for your presentation. I hear that you do other presentations similar to this, other AIA accredited presentations, and we possibly will have you back in the near future if you've got the time.
Absolutely.
So we thank you all for being on this call today. You've got Lucas's information, Michelle's information. She is your architectural rep for Certainty. We will see her live sometime in the early spring. So she'll be doing one of the Certainty road shows and a presentation live sometime in the spring. So thank you all for being on the call. Ron, take us home.
Excellent, Mr. Murphy. And when was that next session, and where is it going to be?
So in February, it's probably going to be February 24th. It's the location to be determined.
Outstanding. So everybody keep that in your
information will be
forthcoming.
Forthcoming, yes.
There we go. So. Well, thank you all for showing up. Those who need AIA credits, please send them to Mr. Murphy or contact. Actually, send them to Mr. Murphy. And with that, we'd like to thank Certainty and Rainbow Restoration for excellent presentations today. Bright Energy, Barton Company, Center for Sustainable Development, Luda Creative Group, and Westchester Home. And last but not least, Mr. Murphy of Murphy Brothers Contracting. Thank you all, everyone. I'm Ron Kamen from Earthkind Energy Consulting saying thank you for showing up. Until next time, take care, be well, and keep dry. Stay safe.
Very dry. Thank you, Lucas.
Thanks, guys. So, folks, most of people here have heard now about New York's Climate Leadership and Community Protection Act, the CLCPA, or the Climate Act. And basically what it does is it puts in place certain rules and regulations regarding what we need to do with our greenhouse gases, and the goals are reductions in emissions, some by 2030, some by 2040. those working in New York City have seen a comparable law in place with Local Law 97, which is even faster. It's actually penalties start in 2024. And as of today, the fact of the matter is that there are hundreds of millions of dollars, actually literally billions of dollars worth of incentives to help organizations, not government, nonprofits, and businesses make the transition to clean energy technologies for your electricity, for your heating and cooling, and for your transportation with electric vehicles and charging stations. However, if we don't start doing it soon, what's going to start happening, and we're starting to see this based into the building codes, is we're going to get hit with penalties. And in New York City in 2024, those penalties are pretty aggressive. What we've seen are penalties to the point of 50 cents a square foot for any space that has excess greenhouse gases, and if you have more than 25,000 square feet. Earth Kind Energy works to represent businesses, government, nonprofit in helping to identify technologies, providers, and financing, including accessing the incentives to make these transitions happen in a way that reduces your cost, gives you a tremendous return on investment, sometimes higher than 20% and more, or for certain entities, can even do it with no cash outlay. So the project gets put in by someone else and they own it, maintain it, and then you just get the savings. So if you're interested in taking advantage of these hundreds of millions, billions of dollars worth of incentives for your electricity needs, your heating and cooling, or whoops, hold on a second. There we go. Someone just needed to be muted. Basically, what these technologies do is reduce your operation and maintenance costs. We access and maximize the amount of utility, state, and federal incentives that you can get. And for those of you that happen to work in nonprofits, a 30% federal tax credit, which is there for solar and geothermal and other technologies that normally couldn't be accessed by either government or nonprofits, is now going to be a grant. So instead of a tax credit, you can actually achieve a grant for nonprofits and government entities. And if you want to know more about that, give us a call. So again, zero cash outlay, outstanding return on investments, minimize greenhouse gases, and create a proud legacy for your family and all future generations. One moment more, there we go. And this is how you find out a little bit more. If you'd like a free consultation, I'm Ron Cammey with Earth Kind Energy. Give us a call, drop us a note, an email, and would love to talk to you about what you're doing and how you might be able to take advantage of a lot of incentives to make this transition to clean energy technologies and go clean, save green, dollars as well as the earth.